Hi everybody, welcome to week 2 of the online section of sept21. In this short video, I'm going to go over a bit of what we've covered this week and maybe some of the stickier points or the muddiest points that you've been posting on the forum. So what have we done this week? Well, we've covered the topics that we've covered are one variable statistics basically, and here's a list of all the topics: 5-number summary, percentile, mean, trim mean, etc. Plots such as histogram, box plots, types of variables, ordinal, categorical, contingency tables, including Simpson's paradox, the definition of marginal and conditional distributions and joint distributions, and observations, observational units, missing values, and the empirical rule. So let's go through some of the points that were posted as the muddiest points this week. So one of the first ones is Simpson's paradox. Well, so how can we understand this and what's the paradox? Well, let's suppose that we have two hospitals and we want to compare survival after surgery in both hospitals. So here we have hospital A, B, and survival. And if they died or survived. So there's, let's suppose that there were 63 people here. 16 people died in hospital B, 2,037 survived in hospital A, and 784 survived in hospital B. So the totals here would be 2,100 and 800, and the total number of patients would be 2,900. Now, so which hospital had lower mortality? Well, it's, let's see, we can compute that by looking at hospital A. The rate is 63 out of 2,100, and that's roughly 0.03. And for hospital B, that's 16 out of 800, and that's roughly 0.02. So we would prefer hospital B. So we would prefer hospital B since hospital B has a lower mortality rate. But now let's suppose that we have information on the health status of patients before they actually had the surgery. So let me just pull out another sheet here. And now let's suppose that we could classify patients into good condition, good health condition before surgery, and poor health condition before surgery. Now we looked at the association between survival and hospital. So now if the data is like this: survival, died, survived, and then we have hospital here, A, B. This is 6, 8, 594, 592, and 600, 600. And now we have a table for those patients that were in poor health before surgery. And so we have a very similar table: A, B, and then died, survived. We have 57 here, 8 here, 1443 here, and 192 here. That gives us 1500, 200. So now Hospital A beats Hospital B for patients in good condition. Since we compare 6 out of 600, which is roughly 0.01, versus 8 out of 600, which is roughly 0.013. And Hospital A also beats Hospital B for those in poor condition, because 57, 1500 is roughly equal to 0.038, and 8 out of 200 is roughly equal to 0.04. So we can see that if we look at the joint distribution, which is back over here, so this is the joint distribution between survival and hospital, and then we look at the conditional distribution of which hospital had a higher mortality. It looks like it was Hospital B. So here, Hospital B. But now if we go and we split, if we had information on their health status prior to surgery, it looks like Hospital A beats Hospital B. And that's the paradox. It's a reversal of an association between Hospital A and Hospital B. That Hospital A, when you split it up, depending on their condition after before surgery, that the association between hospital and survival reverses, and that's the paradox. Okay, and then another point that was brought up in one of the Monday's points is it would find it helpful to work through an example looking at z-scores. So let's work through one. Okay. So suppose that we wanted to compare two tests, the results of two different scores on two tests. So suppose that we have tests. Whoops. Suppose that we have information on tests. One is called the SAT, and the other one is called the ACT. And we have the mean and standard deviation for each test. So the mean on the SAT is 1500, and the standard deviation is 300, and the mean on the ACT is 21 and 5. Now, suppose Anne scored 1800 on her SAT, and Tom scored 24 on his ACT. Who performed better? Well, we can calculate the z-scores. So the z-score for Anne is obtained by taking Anne's score, which is 1800, subtracting the mean, and dividing by the standard deviation, which is 300, which gives us a z-score of 1. The z-score for Tom is obtained by taking Tom's score, subtracting the mean, and dividing by the standard deviation, which gives us a z-score of 0.6. So because, and this basically, the z-score is how many units away, how many standard deviation units you are from the mean. So basically, since Anne had is further away from the mean in a positive direction than Tom, Anne did better. So Anne performed better than Tom. So those are two of the muddiest points that came up this week. And the other one here is how are we going to apply correlation coefficients to problem solving? Well, one of the, basically what we're going to say about correlation in this course is the following. That correlation is the strength of the linear relationship between two quantitative variables. And correlation R is always bigger than -1 and always less than or equal to +1. So a correlation of close to -1 there'd be a scatter plot something like this. So let's say here R would be roughly -0.95. A positive very high correlation would be a scatter plot that looked like that. And so R would be, in this case, roughly close to positive 0.95. And if R is basically looks like a random scatter of points all over the place, then R would be approximately 0. So basically understanding what R measures is how we're going to use it in the course. So R is the strength of the linear relationship between two quantitative variables. Next week, this coming week, the modules have started on probability and events. So I look forward to seeing you online.